video, we'll talk about elasticity and padding and how these, in combination with a few other parameters, can be used to use the kinetic model as a means of distortion. These are kind of related. Both have to do with where the mass is in relationship to the edge of your container. Elasticity defines the bouncing or sticking efficiency when hitting the edges. When set to 0, the spring loses all its kinetic energy when touching the edges. When set to maximum positive value, the spring bounces and keeps all its energy when touching the edges. Intermediate values set the percentage of energy kept when bouncing. Negative values define a sticking force, meaning that an additional force will be required to escape from the edge. It's like the body is glued to the edge. Note that heavy sticking may permanently stick the body on the edge, resulting in a total loss of sound. Now I can say that with elasticity, the results are going to be very dependent on your kinetic parameter settings. You might not perceive very much of a change on elasticity, and if your mass is not hitting the edges, elasticity really won't have any effect. By the way, that's one way you can tell if the mass is hitting the edges of your model. If you take elasticity to minimum and then take it to maximum and you don't hear any difference in the sound, likely you're not hitting the edges. Of course, most of the time we want the mass to hit the edge if we want to have elasticity give us an effect. And one way you can make sure that you're probably going to hit the edge, if you don't think you are, is to decrease the height of your container. Now, padding defines a deceleration area where the mass, in effect, changes properties. Padding, the body can be hard or it can also be soft, metal or foam. When soft, a deformation occurs when hitting the edges, also meaning a smoother deceleration. Therefore, the padding defines a deceleration area when getting close to the edges, avoiding a sudden stop of the motion. Now, the deceleration area can be changed based on the setting of the padding. So if padding is set very low, the mass will only decelerate for a very short distance and you won't get as much of a padding effect. That would be more trying to simulate a harder mass. And if you set the padding to its maximum amount, that'll set the deceleration area very close to where your anchor is, and that will simulate a very soft body. So what are elasticity and padding really going to do for me? Well, one of the things is create distortion in your sound. Let's take our pulsing case as an example. What I've done here is I've created a second shape generator that'll feed the first, so I can basically continually trigger this first generator that's generating a pulse, and I'll keep generating a pulse about every 2 seconds. Then I have a barrel that'll control elasticity and padding. Let's just take a look at elasticity first. So we'll turn on the pulsing. I've set the height very low, so I know I'm hitting the sides here. Let's make elasticity a little negative. We'll stick to the side. There. You can see, with this setting, just a little bit of a change on the negative side for elasticity really just kills the sound completely. As that mass sticks to the edge of the container, I can turn it down a little more, and it basically is totally stuck now. Let's go in the opposite direction. There, we're back to the beginning. Now the mass is losing all of its kinetic energy when it hits the sides, but remember, there's still spring compression, there's still potential energy of the spring, and there's also the potential energy due to gravity that will keep that spring in motion, even though mass loses its kinetic energy. But now we'll turn it up so that we're actually not losing any energy. You can kind of hear there's a lot more active sound. We're kind of distorting things. Turn it up a little more. We've got it to the point now where the model is just oscillating continually. So in this case, I only had to turn it down from 0 a bit to make the sound pretty much mute out, where I had to turn it up pretty high to get that energy effect. Now, as always, if we change the kinetic parameters a little bit, let's increase the height to full. We'll play around with a few of the other parameters. I can easily get this model now to react quite differently for elasticity. Let's set it into motion. I'll bring elasticity all the way down, then I'll bring it up. Okay, elasticity to minimum. Not having much of an effect now at all, whereas before we damped out completely. So here I'm at the lowest setting. It doesn't have much of an effect. Alright, let's go in the opposite direction. Now we're not losing as much energy. We'll set that up to full. Not much going on until I get to full now. And now I can almost hear that I have more energy in the system. Let's take that back to its neutral position. Now let's bring up padding. I can start to see and hear a change. We can hear how that changes the sound from the hard object to a soft object. We'll bring it back. So we can hear a big difference when padding's applied. And padding, remember, you don't have to be hitting walls for padding to take effect. Padding will start your deceleration almost at the anchor point if you set it to max. Let's see how these parameters, especially padding, affect a waveform that's fed into the kinetic model. We'll start with a sine wave with X frequency that will send into the kinetic model to stimulate the anchor, as in the last video. Now I have some barrels to control the elasticity, the padding, and the height of the container. I've set height to be 0, so it's totally controlled by this barrel, set initially to maximum. Padding and elasticity also are set to 0, again totally controlled through the barrels. Padding set to its minimum and elasticity will set to its default 0 position. Let's see what happens to this sine wave as we apply padding to it. Okay, there's our sine wave. We'll bring up the padding. We can see we're starting to distort that waveform more and more. You also can see that the waveform is getting lower in amplitude as it distorts. And there I'm at max padding with basically a totally distorted waveform. That deceleration will produce this decrease in amplitude, of course. Let's see what that looks like on the spectral analysis tool. Our single harmonic starting out. You can see how we increased the harmonic complexity there. Now something else we can talk about is height itself. Before we only talked about this in relationship to how it reduced the amplitude of the signal. But when you think about it, if I reduce height and the mass starts hitting the walls, I should also distort that signal as well as simply reduce it in amplitude. Let's give that a shot with our sine wave. I'll lower the height, and we can see it's starting to deform the waveform. As I continue to decrease the height, of course, I can basically reduce the sound to its bare minimum, where that mass only has a very small space to move. Now let's apply elasticity to this constant waveform feeding my model. What I'll do is I'll lower height to the point where I can hear it change, and then I'm pretty sure I'm hitting the sides where elasticity can then take effect. Alright, there's my sine tone. Let me lower the height. There, I'm pretty sure I'm hitting the walls now because I'm seeing that distortion. Let me lower elasticity. I'm seeing a change in the waveform. Let me raise it. I can hear at the top there, I can hear that distortion in the background, as I know that I'm not losing energy at that point when the ball is bouncing. I can change height a little lower, do the same thing. I'm already distorted, remember. Bring down elasticity, and there, it's stuck on the wall. I'm not at my minimum point yet. Once again, the combination of parameters that you set are going to have a great effect on how elasticity performs for you. You just have to experiment to get to a point where it's doing what you really want it to do in terms of distortion. Let's see what happens now when we send in a more complex audio signal. We'll take the sine wave, set the spectral balance to 0.7, which is in that sawtooth area. Let's just listen to what that sounds like. So there's our basic complex waveform with all of the spectral components showing. Now let's feed that into the anchor position as we did before. We have frequencies set here to 440 Hertz. Let's see the result now. As in the last video, you can see we have these spectral enhancement areas, a spectral peak here, a little more than 2 kilohertz. We can adjust that by offsetting the frequency in combination with some of the other parameters. So we'll set that to 2.5, and this will, in this case, have an effect of evening out that spectral plot to be kind of similar to what the base waveform was. This you just have to experiment with. Now let's bring up the padding on this. You can see that it distorts the waveform. This actually didn't start until I was about 3/4 the way through the padding number. Let's do it again. We'll decrease the height of the container. That'll distort the waveform to begin with. See what happens here now. In this case, it started to take effect now even sooner, about halfway through the padding number, and it seems to be even more distorted because we started with a more distorted signal due to the decreased height. Again, you just have to play around with padding. In this case, it's going to be a source of distortion for you, which you could find appealing in a lot of sounds. Let's remove the padding. We'll take the height up, and now let's play around with elasticity. As before, we'll decrease the height until we see a change in the spectral content, which means we're probably hitting the edges, and then we'll play around with elasticity. There I can see a change. Now let's lower elasticity. You can see it got to a point where it stuck to the wall after distorting from the beginning point. I was only at about minus 0.5 there when the sound tonally went away. We'll take our elasticity back to 0. Now let's increase. Not much difference in this case. If we take height down a little more, now let's bring elasticity up from 0, see if we see more of a change. So for this combination of parameters, it appears we get more of a distortion effect when we take elasticity in the negative direction, in the sticking direction, than in the positive direction. And perhaps that makes a little sense because the waveform is already quite energetic with all the harmonic content. And even though now I don't lose energy when the mass is bouncing against the edges, there's less of an effect. Now if we take things back and apply noise instead, you'll see that padding and elasticity have much less of an effect because of the random variation that's already there. Now there's our noise. Let's bring up padding. Doesn't do much. We'll decrease height a bit. That obviously is going to decrease amplitude. Let's lower elasticity. We'll raise elasticity. So as you might expect, elasticity and padding would have less of an effect on noise where you already have a lot of distortion due to the randomness of the signal. Let's see what happens when we apply the padding and elasticity to a vocal phrase, or the additive synth bank in this case. We'll create a shape generator that'll take 10 seconds to move through the additive modeling phrase. We'll create a formula with a ramp from 0 to 1 that'll move through that phrase. We'll put that on the index to the additive bank. We'll use W to trigger the amplitude of the bank and set the frequency to X. We'll put that on the input to the excitation column, and then we'll play around with padding and elasticity. So our base phrase,
did you ever have a feeling that you wanted to go and still have a feeling that you wanted to stay?
We can control the pitch of that with X now. If we look at the kinetic properties, I've set viscosity rather high here. If I set that too low, I will hear a ringing effect.
Did you ever have a feeling that you wanted to go?
As we decrease the friction there. You may well like that sound, but we'll set it to where we had it because we want the phrase to be heard as is.
Did you ever have a feeling that you wanted to go?
And now I'll bring up padding on that.
Did you ever have a feeling that you wanted to go and still have a feeling that you wanted to stay? Did you ever have a feeling that you wanted to go and still have a feeling that you wanted to stay?
You can hear the distortion that's applied there. You still can hear the phrase come through the way we have it. I've set the height so it's a little lower so I can kind of predict I'm touching the edges for my elasticity parameter. We can even set that a little lower. Put padding back. Now we'll play with elasticity.
Did you ever have a feeling that you wanted to go and still have a feeling that you wanted to stay? Did you ever have a feeling that you wanted to go and still have a feeling that you wanted?
Not much of a difference for these settings. So as I said before, elasticity, you really have to play around with. Some settings you'll see a lot of change, other settings you won't. This is perhaps not so useful as a sound long term. Perhaps what I could do is set this to a fixed value, say 0.6, instead of ramping through that additive set. So I'll set myself on an index right in that set. A more useful sound perhaps. Let's bring padding up on that. I can definitely hear more of a distortion effect there in that case. Let's set the height down. Maybe we'll bring up the gain a bit. And we'll play around with elasticity. Maybe a subtle change there, but again, elasticity for this combination of parameters is not really having that much of an effect. But I can play around with the parameters, set viscosity low, set height really low, and now elasticity will have a greater effect. If I go negative, I really can hear a big change. And now I'm hitting the wall and I'm totally stuck. Let's go in the positive direction. There's my 0 point. Not so much change in that direction, but big change in the negative direction. So once again with elasticity, you have to play around to get to your sweet spots of where that sound is going to work best for you. What we'll do is stop here so we can reserve the last video to talk about perhaps the most interesting feature of the kinetic model, and that's the slipping friction and bowing related components, which really take this quite far afield from the classical spring simulation we've been looking at in the first few videos.